Okay, this is component 3 Mock 2 and we're on paper 2, question 2. That person bursting in was Dr. Sowell again. He likes to burst in. Okay, so we've got a picture of, and it's a weirdy one, of a double circulatory system. So you've kind of got to work out what's going on. So here we've got the heart in the middle. So this is the right atrium, right ventricle. So we've got blood flowing in, so this is the vena cava, and it's flowing in from there as well, so that's the vena cava. It's going out of the right ventricle and splitting there, so that's the pulmonary artery, that makes that the lung capillaries. That's the pulmonary artery, the other branch going the other way, so this is lung capillaries. And this is the pulmonary vein, going back into the left atrium, left ventricle, out through the aorta, no, not going out through there, going in through there. So that's the pulmonary vein, coming down through here, out through there, so this is the aorta, going up to the head, presumably, and back down superior, and then down to all the body tissues. So all of these little things here are capillary beds. Okay, so and sorted that out. Using only the letters A to G, identify the following. Letters may be used more than once. Used once, more than once, or not at all. But you've got two things there, so that's a bit of a giveaway, isn't it? Parts of the pulmonary circulation then. So this is our pulmonary circulation. It's going along there and back round. So E is definitely a letter. And then coming round here and going back round, and so D is definitely a letter. Now obviously the examiners would probably have preferred it if you put those in alphabetical order. Blood pressure is maintained by elastic recoil. So here, what are we looking for? We're looking for arteries. So which are our arteries? So we've got this artery, D, and this is another artery, and that's not labelled anywhere else, is it? C. Again, probably be better if those were in alphabetical order. Blood flow is maintained by contraction of skeletal muscle and breathing movements. So here we're looking for veins. So which are our veins? Veins are flowing in over, so B is one. Going into the right atrium. We've not got a label here. We've not got a label there. Dash, that's awkward, isn't it? So coming back in, following it back round. F. Oh, and that randomly does end up in alphabetical order. Happy examiners. Okay. So then we've got what we got. To answer the questions that follow, so we've got aorta, other large arteries, arterioles, capillaries, number of vessels, how long they are, how wide they are, total cross-sectional area, total blood volume and rate of blood flow. So going fastest in the aorta and slowing down. Blood volume going up, down, up. Total cross-sectional area with a big blank. Mean diameter going down, mean length going down, total number of vessels going up quite dramatically. Okay. Using the formula below, calculate the total cross-sectional area of the capillaries. So if we're doing the total, we need the area of the capillaries and we need to know how many there are. Then it tells us to do it to 3 significant figures. They're obviously expecting us, I think I might need a better calculator than this actually. Anyway, so it tells us what to use for our cross-sectional area, so that's pi r squared, so that's 3.142 times radius. The mean diameter that we're looking at is 0.0008, half of that. I'm going to do that in my head. Is that, and we need to square it. So let me have a look, see if my calculator is good enough to do this. 0.0004 times 0.0004. Oh, probably not, because I don't think it's giving me enough decimal places. No. Okay, I'll have to look at the mark scheme then. So that works out to 5.03 times 10 to the minus 7, or you could write that as 0.00000005. Interesting. You're then going to need to multiply that, so I'm just going to call that ants, because otherwise I'm going to run out of space, by the total number of capillaries. Now again, my rubbishy calculator, it doesn't have enough decimal places on it, and it certainly doesn't do to the power, so a scientific calculator would be your best thing. That would give you an answer of 603.264, and then you need to make it 3 significant figures, so that's the first 3 numbers, 603. Job's a good one. 1 mark for putting your numbers into there and realising it's 0.0004. 1 mark for multiplying it by the total number of vessels and getting that. And the 3rd mark for putting it to 3 sig figures. So moving on, explain why a low protein diet would result in fluid retention in the tissues. And we certainly did this as one of our sort of examples of how you might get edema. So, low protein diet. So low protein causes a lack of plasma protein, is the first thing to say. So if you're not going to protein in your diet, you're not necessarily wasting it making plasma protein. Usually, what's the role of those? Usually plasma proteins lower water potential in the blood. And that of course is significant at the venous end. This is a lovely logical argument. So if plasma proteins are lacking, the water potential of blood is higher than usual. And of course you could write less negative there. So why is that important? So this means the water potential gradient between tissue fluid and blood is not as high. And at the venous end, not as much water is reabsorbed, so remains in tissue fluid. So that I think is a really good example of sort of telling a story in a nice logical order. So, the idea that if you've no protein, then you've lack of plasma proteins. What do they do usually? What happens if they're not there? So it's the not story again. If plasma proteins are lacking, this happens. What does that mean? What happens? How does that cause fluid retention? And it's just like the perfect question.